Okay, so today, building on the last lecture, will be about incorporating negative edge lengths into our shortest path algorithms, shortest walk algorithms, as well as the related all pairs shortest path problem. So just to quickly remind us, we've been doing directed graphs or graph stuff for more than a week now. So last week, today, was when we did depth first search and reachability, strongly connected components, stuff like that. Whether A can get to B, point A can get to point B. And then last time we got greedier and asked not only can point A get to point B, but what's sort of the fastest way to get there if the edges are marked by lengths or something like that. So that was like breadth first search and Dijkstra's algorithm. My guess is that many of you have seen most of these algorithms in some way or form before. Okay, but a big thing in last time's class was that all the edge lengths, or even in unweighted case implicitly, were positive. Okay, so today we're going to remove that assumption, explore some of the consequences and nuances. So, right, I want to just incorporate negative edges. So here I took, I think, the same graph we've been using all the time, and I've added some negative edge lengths in addition to positive. And now the question is, what's the distance from S to T? What's the minimum length way to get from S to T? Okay, so now you just add up the numbers, and it might be a negative number. It might be negative infinity if you find a cycle, negative cycle. All right, so I'll give you guys a chance to stare at it, and then we'll try to guess at what it could be. All right, I heard 0, so how many people got 0? All right, how did you get 0? Just tell me where to go. I'll start at S. Right. Okay, let me do it this way, like this. So 3 minus 2 minus 1, that gets me 0 total. Okay. Can anyone do better than 0? Okay. Okay, so here's like a nice negative 10. That's like worth a lot of points. Oh yeah, okay, I forgot. Let's say that yeah, let's say that that's negative 3 and that's also negative 3. I don't know. Huh? So we'll go this way, you're saying? Uh-huh. All right, so this adds up to 1 minus 10, 9, 12, 11, 9, negative 10? Okay. Hopefully negative 10. Hopefully we're not off by much if we are off. Okay, so probably less than 0. Can anyone do better? Yeah, I personally don't spawn anything better, but again, that's hardly a certificate, right? So it's always funny how it's hard to verify a solution by eye. Okay, so hopefully that made you think a little bit longer than if it was just strictly positive edge weights. So, all right, just to explain why what we did last time doesn't work, here's sort of the simplest example I could think of. Suppose I ran Dijkstra's algorithm, I just ran the code. Okay? It's a relatively simple graph. There's only 4 vertices. There's no negative cycles even, just one negative length edge. If I ran Dijkstra's algorithm, starting at A, to find a distance to D, what would it tell me? Two. So let's walk through what it would do, right? First, it would start with A and say, okay, that's distance 0, right? And then it would find the next one, and that's B at distance 1. Okay, and it'll find kind of the next closest, and that's D, and it'll say it's distance 2. And it'll decide that this D is at distance 2 before searching C, discovering it's distance 3, and finding out, oh, you can actually go back in time, right? And you can do 3 minus 2 and get to 1. But Dijkstra, it just does one pass through. It's kind of overly aggressive, and it wouldn't catch this negative edge. Okay, so something broke. All right, the other subtlety that comes up with these negative edges is the possibility of negative cycles. So here's sort of a simple example. So what, by definition, is the distance from S to T in this graph? Yeah, so, okay, it could be 3 because I can just go straight across. It could be 1 because I can go, 1, 2, 3, 0, 1, 2. That would give me 2. It could be, I guess, 0 because I could go 1, 2, 3, 0, 1, 2, negative 1, 2, 1, 0, 1. Okay, it could be 1, right? But the point is, every time I go around the triangle once more, the total goes down by another negative 1. In particular, it's smaller than any finite number. It's smaller than negative 10, it's smaller than negative 11, smaller than negative 580, right? So if there's no lower bound, we call that negative infinity. Okay, so when there's negative edges, you can have negative cycles, and then you get funny stuff like this. Okay, so some of our intuition sort of breaks a little bit. This isn't quite like geometric distances because there's no negative geometric distance and stuff like that, right? But nonetheless, it's also a natural problem. Okay, so, all right. So that's right. So in the presence of negative edges, and just still wanting to compute, distance from S to T, otherwise same question as last time, we get these sort of weird questions, right? Questions like, how do I deal with negative cycles? How do I find them? How do I avoid them? What happens when they come up? Another question that sort of didn't arise last time is that if everything's a positive edge, and we'll do a proof in a moment, there's no reason to have a cycle, right? Like repeating yourself is just going to add lengths. So at some level, when we're trying to find the shortest distance, we were only really worried about paths. There's no reason to take something that wasn't a path. The difference between a path and a walk is that a path doesn't repeat vertices, a walk is allowed to repeat. Okay? So, okay, what's going on? Now with negative edges, there is actually sort of a greater distinction between walks and paths, and can we figure out what's going on and when? Okay? And maybe another third question is, more subtle. When we were analyzing breadth first search in Dijkstra, we had this like very clean approach of like kind of building out, I know that S is the closest vertex to S. And from there, I can figure out the first closest vertex, and then the second closest vertex, and the third closest vertex. And we had this nice, strategy, and it was accompanied by an equally nice proof, right? And that approach, building up from 0 on out, was sort of the induction, how we proved correctness by induction. But that logic broke here. So we'll need to come up with some other way, to somehow think inductively about the problem that's different than what we did last time. Okay, so 3 basic questions. Okay, so we're going to address roughly the first 2. First, trying to just figure out structurally, not really worrying about algorithms right away, just what's going on with negative cycles, negative distances, and just try to get a good understanding of this negative infinity phenomena so we can think clearly about algorithms afterwards. All right, so, let's just start with the claim. All right, suppose I have 2 vertices, S and T, and S can somehow reach T. So I'm not worried about the case where the distance is positive infinity. Okay. All right, I'm trying to understand when is the distance finite and when it's infinite. The claim is that the distance from S to T is finite. Okay, it's something not negative infinity. If and only if the shortest walk from S to T is a path. Okay, and so in other words, there's a path from S to T that attains that finite value. Okay, so it's just a structural thing. It's not an algorithmic thing. The distance from S to T is finite if and only if that shortest walk turns out to be a path, or could be a path. Okay, does the claim make sense? Okay, so a path, walk is just any way to get from S to T, but it can repeat. It can revisit the same vertex. A path is like a walk, except we're not allowed to repeat vertices. Yeah, so a walk can go like that, where I'm revisiting that vertex and that vertex. But that's not a path. A path should be all distinct vertices. Yeah, okay. So yeah, the definition of distance allows you to repeat vertices. So structurally, this is saying the distance is finite if and only if that shortest walk doesn't repeat vertices, or at least there is a shortest walk that doesn't repeat vertices. Yeah, so yes, we will address that in the proof. Yeah, perfect. Okay, good. So, all right, so the claim is it's finite if and only if it's a walk, if it's a path, okay? So one direction is sort of not too difficult. Suppose there is a path from S to T that gets you that distance, right? DST is equal to the length of that path. Well, any length of any path is finite. Okay, so that's like not very big claim. Okay, so one direction is sort of trivial. If there is a path from S to T that gets where the length is equal to the distance, then of course it must be finite. It's so okay, not very interesting. Here's the more fun direction. All right. Okay. Now suppose the distance from S to T is finite. Okay, so there's some number L, there's nothing smaller than L, and there's walks of length L from S to T. This is the interesting direction of the claim. Okay. All right. I want to argue that because it's finite, I can actually get from S to T along a path with total length L. Okay, so we know there's a walks out there of length L, and I want to argue there's a path of length L. Okay. All right, so we're going to let W denote some walk of length L. Okay, but out of all the walks of length L, let it be the one with the minimum number of edges in it. So there may be many ways to add up the edge lengths to L, whatever L is. L may be 0, L may be 10, L may be negative 10. But among all those walks tied with the same minimum distance, pick the one with the fewest number of edges. Okay, there's always some minimum because there has to be at least 0 edges. Okay, so there's always something that's going to get you the minimum number of edges. Okay, so, and suppose that W is not a path. If W is a path, we're just done, right? Because that's going from S to T, and it's a path, and it has length L, so we're done. All right, so an interesting case, W is not a path, it has some cycle C. Okay, so I guess in this picture, there's some cycle I'll call C. Okay. All right, so we have 2 cases, and I'm going to let you guys tell me what to do in each case. Okay, so the 2 cases are, we're going to reach some contradiction in each case. In one case, the length of the cycle is non-negative. If I sum up all the edges along the cycle, I get something that's greater than or equal to 0. In the second case, the length of the cycle is less than 0. If I sum up the edges along the cycle, the total length is less than 0. Okay, each of those I'm going to reach some contradiction. Okay, all right, let's start with the first case. What if the length of the cycle is greater than or equal to 0? What can I do that creates a contradiction? Okay, so if I looked at this walk, which kind of skips over the cycle, so I remove the cycle. It might not even be a path afterwards because there might be other, loops I didn't draw. But nonetheless, since the length of the cycle is greater than or equal to 0, removing that cycle, I'm just subtracting some non-negative value. So the total length of the walk is not going to go up. On the other hand, I have strictly fewer edges. But W was supposed to be the one with the fewest edges among that length or less. So there's our contradiction. Okay. So if that cycle was non-negative, I could remove it and decrease the number of edges without increasing the length. And okay, that contradicts our choice of W. All right, that's case 1. Case 2, the cycle has negative length, total length. Right? You kind of go back in time when you go around the cycle. All right, now how do I reach some contradiction? Yeah, okay, so this is not the minimum. So you guys are all right there. How do I express this? Why is it not the minimum? Yeah, so we can make a better one, like if it was in this example, if I repeat the cycle, so I go around once and I go around twice, okay, the total length has gone down. All right, so if it's something less than 0, I could repeat the cycle, the distance goes down, but W was supposed to be the minimum distance. That's an issue. Yeah, there could be multiple shortest paths. Yes, that's right. That's right. That's right. So even if the cycle had length 0 or something, we're not decreasing the distance or anything. There's walks that are tied with the path. But the point is there is a path, okay, that gets you to minimum distance. So why does that kind of practically matter, right? Is because how many edges could be in a path? What's the maximum number of edges in a path? Yeah. Yeah, n, because there's only n vertices. In fact, you can do a little bit better. There's only n minus 1 just because the one gets trimmed, right? So that means I only have to worry about walks with at most n edges or something like that. But if that wasn't the case, if we didn't have a lemma like this, and I had to worry about walks with, I don't know, 10 n edges or n squared edges or some huge thing, we potentially might have to search the graph for a long time just to make sure we cover enough edges, right? So this is important to get us set up for the algorithmic discussion next, because at some level I only need to worry about walks of length up to n or n minus 1. Okay? If I'm just trying to figure out who has finite distance. Okay, so yeah, you'll see, we'll use this a lot. This is the one structural thing that we need, and it's going to clear up all this confusion about what happens with negative cycles, what happens with negative distance. We'll just rely on this lemma. Any questions? Okay. All right. So that sort of addresses some of these questions of like, okay, what happens if there's negative cycles and we get negative infinite distance, stuff like that, and what's going on between shortest walks and shortest paths. In fact, we only need to worry about paths if I'm just trying to figure out what's finite. Okay, so basically there's only two cases. One, there's a negative cycle along the way and you get negative infinite distance. Or there's no negative cycles on the way and it's just a path, right? There's like a nice dichotomy. All right, so, okay. Now let's move a little more algorithmic, which sort of brings to the fore this question about, how to make an algorithm again, and in particular, how to come up with some kind of constructive strategy. Yeah. Is there a case where the shortest walk is not attained by a path? Uh, so essentially what the lemma is saying is kind of like no. So basically there's two cases. Well, I guess there's three cases. One, A cannot reach B. So there's no walk from A to B or path, right? Case two is that the minimum distance, the distance is finite, okay? In which case, there may be walks that are good too, but there's also a path that's minimal. Case three, the distance is negative infinity, in which case there's really no walk that gets you negative infinity. You can get arbitrarily close because you're using some negative cycle along the way. So it really breaks it down into only three possibilities. So I think the answer to your question is no. Okay. All right, so we have a little bit more of a structural understanding of what's going on here, negative edges. We're moving on to this algorithmic question, which also has a lot to do with, okay, how do I make this kind of constructive? How do I build an algorithm, right? Because I know that this Dijkstra strategy, we already saw a really simple example, is not going to work. This breadth first search strategy, building out from closest to furthest incrementally, right? Sort of a greedy strategy, sometimes it's called. That's not going to work. That we already know, right? So, any ideas? Yeah. Okay. Okay. Yeah. So this is not a bad idea. This is often suggested. Okay. So if we look at this example from earlier, I guess the minimum weight is like negative 10. So in other words, the natural thought process is, can I reduce to the the positive case or non-negative edge weight case, right? Because we know how to deal with positive weights. So can I reduce it? So let me look at this, figure out what the most negative edge weight is, negative 10, and say, okay, I'm going to add 10 to every edge. Or if I want to avoid 0, I'll add 11. All right, so I'll add 11 everywhere. Okay, I can add 11 to the weight of every edge. Now everything is at least 1. Okay, so you get the idea. Okay, so that's a natural idea. This often comes up. So I'll add enough. I'll add the same amount to every edge to make everything positive, and I'll run Dijkstra's algorithm. And Dijkstra's algorithm always works on positive weight graphs, right? All right, but why won't this work? Yeah, I don't know how much to subtract from the final answer. Why? We don't know the number of edges. So this treats every edge equally, but it doesn't treat every path and walk equally. If I have a path with 5 edges, I'm adding 55 points. If I have a path with 10 edges, I'm adding 110 points. Okay, so this is actually biased towards the paths with fewer edges. Yeah, it's a good idea though. Any other ideas? It's not easy to guess, but once I reveal it on the next slide, you'll never get to guess again. So, could be totally silly ideas, just for fun. All right, so let me present a different kind of related problem, but a little bit more conservative. Okay, so here's a different perspective. Okay. Suppose I added like some parameter k. Okay, like k could be 10. And I said, what is the shortest way to get from S to T with at most k edges? Right? K could be 10, k could be 100, k could be n, right? So I've actually added a parameter to the problem, which you guys may have done in your homework last week, right? So I actually added a parameter to the problem. So now slightly different problem. We'll figure out how to connect it to the original problem later. My goal is to go from S to T with set most k edges and minimum total length. Okay. All right. Okay. If I wanted to solve this problem, how might I go about it? Or what might be a natural strategy? Something that I can maybe make some induction argument on. Yeah, okay, or let me put it another way. What values of k is this really easy? Start with 1. K equals 0 is also really easy. Don't use any edges. K equals 1 you also know how to do. All right. So now the big challenge is how do we do k equals 2? Yeah. Okay, so now we maybe can use k as the basis of an induction argument, right? I could do k equals 0. Once I figure that out, do k equals 1. Figure that out, do k equals 2. Okay. All right, so to that end, we need to, well, if we're going to do some kind of recursive inductive algorithm, we need to start with a recursive spec. So what's, anyone want to suggest a sentence? Okay, good. So you can always start with basically restating the problem. So just tell me out one part. So okay, length to the shortest walk from S to T without most k edges, and yeah, shortest, so minimizing the length. What are the parameters of your sentence? Like what are the parameters? K. So S and T are fixed. You're saying okay. So we can do SWK is equal to length of the shortest walk. All right, SW from S to T with at most k edges. Okay, so our parameter is k. All right, so let's imagine implementing this. So SW of 0, right, would be, sorry? Our recursion will be a problem because? Because we fixed the endpoints. Yeah, so k we want to be in there, but right now I can't change S and T because it's not parameters. Okay, so what can I do? Oh, okay, we can add T. Okay. SWTK will be the length of the shortest walk from S to T without most k edges, where S is fixed and T I can vary. Okay, it's the only difference. All right, I think that's close to what I had written down. Okay, so yeah, exact same thing. Length of the shortest walk from S to V without most I edges. Okay, seems natural that V is going to be useful because then we can choose our intermediate vertices, right? Okay. All right. So if we want to implement this, help me implement it. Sure. Just tell me what to do. Okay, so if I is equal to 0 and V is equal to what? V is equal to S, then return what? True? 0. Okay. All right. If I is 0 and v is s, then I'll return 0. Okay, that's one nice base case. Any other nice base cases? Okay, so if I is 0 and v is not s, you don't have any edges, right? So it has to be positive infinity. Okay, great. I think that's all the base cases I had in mind, unless I'm forgetting one. Okay, so now in the general case, let's say that I is at least 1. 1, 2, 3, 4, 5. Okay, yes, I think you're saying, okay, so I want to get to v, right, starting from s, and we can try to guess which edge going into v to use for like the last step, right? And then from here, to u, that's k minus 1 edges, so I can do some recursion. Okay, so we can write the minimum over, and I'm going to introduce some new notation. So uv. So sometimes people use this kind of partial or as a fancy notation for all the edges going into v. This sort of calculus-looking thing. Okay. So I'm taking a minimum over all the edges going into v. And recursively, how do I get from s to u in I minus 1 edges? Plus, I add the length of the edge from u to v. Right? Okay. All right, does that look good? We're actually missing one thing. Okay, so you don't have to use the 10th edge. Maybe the best is just 9 edges. Right? So we can also compare it to not using that last edge. Okay. Yeah, so the sentence actually says I'm allowed to use at most I edges. So if I don't want to use I, then I use I minus 1. If I didn't have that, we would always be calculating the number of the shortest distance with exactly I. Now this is at most I. Okay. All right, simple enough code. I think that's what I have. Yeah, good. It's just more colorful. All right. Okay. Good. So that's kind of nice and simple. You'd have a nice simple, I didn't write the proof, but the proof would just be by induction on I, right? Because I know I do I minus 1 correctly. That lets me argue that I can do I correctly. Okay. All right. So nice and simple. How long will this algorithm take? So it's kind of like dynamic programming, assuming I do caching, right? I'll save all my answers. Why not? So it's like dynamic programming, although this time it's not just on a sequence. So it's going to be a little bit more involved, but it'll be similar. So if I want to calculate the running time of this, well, I'll just sum up over all the subproblems, right? So, all right. So here, I'm summing over, let's say I'm just going to try to get k. So I'm summing over all choices from 1 to k, and then summing over all the vertices, and the time I spent on SWVI, right? I'm just summing up the running time for all the subproblems. Okay. So for a particular vertex V, because it's kind of the same for all I, how long will it take? Yeah. Yeah, and in particular, yeah, so each of these is, the code is basically just a loop, right? I wrote it as a min, but that's really looping over all the edges going into V. Okay, so this is uh, called the in degree, not the out degree. It's called the in degree of V. The number of edges going into V, the number of edges going out of V would be called the out degree. If it's an undirected graph, it's just called degree. Okay, so for every vertex, and I'm multiplying by k because there's k choices of I, it's some constant 1 plus the in degree of V. Okay, all right. If I sum up the in degree of V over all the vertices, what do I get? Number of edges. It counts every edge once. Okay. So all put together, oops, the running time is k times m plus n. Okay, so we need to justify how big I need to make k. So this is still just solving this sort of auxiliary problem about most k edges. Now we're going to shift into relating it to how to get shortest paths and walks. Well, even if a vertex didn't have any edges coming in or something, you'd probably still do a constant amount of work. Yeah. Yeah, they're just representing base cases or whatever. Okay. Yeah, it's just worried about the case of in degree 0. Yeah. Uh, so why are we just using the target? Well, I guess in this case it's sufficed. Here okay, so if I actually want to get the ST walk was at most k edges, I would call SWTK. We know we need at least one parameter to be able to guess the intermediate ones. And I guess this shows that you don't have to include the source, or you could have included the source and we kept S the same. Yeah, we could have also done it backwards, where T is fixed. I'm gradually kind of adding to the beginning, or from your perspective, I'm adding to the beginning of the path. But still going this way. Yeah, this is not the only way to do this same high level idea. That's right. In fact, later we'll talk about with all pairs shortest paths, we actually will have both, but we'll get there soon enough. Okay, so let's work our way back to the original problem. Okay, so all right, so we've done two things really so far in this class. One is that we have this characterization of finite distances, right? S to T is has finite distance if and only if that distance is attained by a path. And then we have this dynamic program, kind of recursive algorithm that can get me walks for any particular value of k. Of course, the bigger the k, the slower it gets. So ideally, we like to kind of find a small choice of k to solve our original problem. Okay. All right, so let me start with a simple case. Suppose there's no negative cycles in the graph and everyone has finite distance. There may still be negative edges, okay? But otherwise, all the distances are finite or plus infinity or something, right? But there's no negative infinity. Okay, if I want to get the distance from S to every other vertex T, and I'm using this dynamic program, how big does K need to be? N. Or for the really OCD, N minus 1. Oops. Okay. For all the vertices V, will give me the distance to V for every V, right? Because I know, because it's finite, everything is a path. N minus 1 edges is enough. N edges is enough. Okay. And we're okay. All right. So if I promised there was no negative cycles, then we know how to solve this thing in roughly mn time, right? Because I'll set k to be n. Okay, great. Now, okay. Now I'm going to remove that promise. Yeah, assuming m is larger than n. So sometimes I get lazy. You could have run like depth first search from S at the beginning. That only takes m plus n time. Throw away everything that S can't reach. In the remaining graph, m will be at least n minus 1. Okay. All right. Okay, so I'm going to remove, actually, let me ask you guys a question first. Now, suppose I remove that promise that there's no negative cycles. There could be negative cycles. Okay. Now we have questions like, how big do I need to make K? Do I need to run it forever? How do I find a negative cycle? Right? How do I, even if I found a negative cycle, I have to figure out everything on the other side and stuff. How do I know there's no negative cycles between S and T? How long do I have to run it? To feel like I've really searched everything. Obviously, the bigger the K, seemingly the more it would help. But is there an upper bound on K? Contract to connected components. I mean, the whole graph might be strongly connected. With maybe very big, nearly infinite weight edges that don't really help you on any shortest path, but otherwise, so I could have given you a complete, I could take a regular graph, my input graph, and then add edges between every pair of vertices that doesn't have an edge. Make the weight so big it's useless for any path. Now the whole graph is one strongly connected component, so it won't help you to contract it or something like that. Yeah.
For every vertex, you could run shortest walk from it to itself with length n minus 1. And if one of the vertexes is in a negative cycle, it'll return a negative number.
Okay, good. So if there's a negative cycle, there's in particular one that doesn't repeat itself. Okay, so I can go to every vertex V and run SW NV or VN to see if I can go from V back to itself and go back in time. Okay, and so I find a negative cycle. And then from there, I identify all the vertices that participate in negative cycles. I can figure out like, who this vertex can reach, and which vertices can reach that negative cycle, and then all those distances will be negative infinity or something like that, right? All right, how long would that take? Even just the first stage. So for every vertex, I run our algorithm. Yeah, like what? Mn squared or something like that. So originally we had Mn for one fixed choice of S. Now I'm running it from everyone, so I get another N, and I get like Mn squared. Yeah.
How about just storing the information about which 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 versus used for specific work? I mean that we just get only interested in a path. So I hope we can find the duplication if we store information with vertices.
Sounds complicated. Yeah.
When you are on the path, you can mark the ones you have visited, the ones you have visited as visited, and if you visit someone that you visited already, you can just mark that particular path as just distance infinity. So you just don't go on it further.
Okay. So can you do some kind of marking and keep tracking of paths and stuff like that, and have some reverse pointers?
For that particular path, keep track of the vertices you've already visited.
So there's a couple of things we need to be careful about, right? So if you look at like a recursive algorithm, right? At some level, the entire state needs to be captured in that sentence. Because if you're kind of marking things under the hood, now things are changing and we have to account for that in the proof. That's one tricky thing. Another thing is that there's no unique shortest walk from A to B with 10 edges or something. So does marking in one way instead of marking in a different way lead to different outcomes? Depending on what you wrote, finalize your code to be, that could be an issue. Yeah.
One thing I consider on the negative cycles is in ON time, already removed.
Yeah.
And that'll identify the cycles from there. We just have to search those cycles for negative values. So it would be O n time to find the cycles.
Okay. It's kind of like imagine running depth first search, and whenever I'm about to go back to a marked vertex, marking is like removing. Ah, I found a cycle, right? So a couple questions. Are you really exploring all cycles?
Well, it would have to go back to something that was removed in order for it to be a cycle. Otherwise, it would all be point of a signal, right?
Well, let me suggest this. There could be, take a complete graph with edges going both directions between every pair of vertices, right? There's like 2 to the n cycles, or probably more actually. Choose any subset and then any permutation thereof of the subset of vertices will give you a cycle because you have all the edges and whatever you want, right? So if your algorithm is really enumerating all the cycles to check what's negative, it's going to be taking that worse than exponential time. But I also don't think your algorithm is enumerating all cycles because it's doing depth first search, so it can't be slower. And what it's kind of doing is carving out some particular path, right? And it's checking the cycles that involve that path, but there's other paths that you don't fully explore because they've already been marked, right? They've kind of been cut off. Can you imagine? So yeah, anyway, so yeah, you won't explore all cycles, plus if you explored all cycles, that's even worse. Okay. All right, so what we're going to do is we're going to try to argue something more subtle. So, okay, the punchline, should I say the punchline? Okay, no, we'll wait. Okay. All right, so we have to be careful, though. I think at the very least, it's clear it's a little bit subtle, right? How to figure out these negative cycles and stuff. We can pay an overhead of an extra factor of n, and that's what I'm going to try to avoid. I want to do something more slick than that. Okay, so I think the key part, at least this is how I proved it. Maybe there's maybe other ways in textbooks. I mean, none of this is new, of course. All right, so I'm defining the set A sub k. These are the vertices where the kth edge decreases the distance. Okay, so these are the vertices where the shortest walk from S to V with k edges is strictly less than the shortest walk from V to k minus 1. That kth edge helped for that vertex. Okay, so A sub k are the ones that keep improving in round k. Right? Okay, so for example, what do I know about A sub n? So these are the vertices where the nth edge decreased the length of the shortest walk. What happens if a vertex improves on the nth edge? Then what? Well, it could be that the edge weight would be, no, it doesn't mean that the nth edge is negative. It could be coming from some other neighbor that's just really small or something, right? A positive edge from a small neighbor. Or I can exaggerate more. What about A sub 2n? What happens if on the 2nth edge that length went down? Yeah. So why is there a cycle? How do I know there must be a cycle? Okay, that's the right idea. So let me say what you said, but slightly differently. If the distance from S to V was finite, that nth edge shouldn't be able to help you, right? Because the path should be good enough. It should have stopped at n minus 1 and never improved afterwards. So if it improved on the nth edge, I immediately know that the distance is negative infinity. Okay, so our lemma says that if I have some vertex t in A sub n, that means the nth edge helped. I already know the distance is negative infinity. Right? And what about A sub n plus 1? Well, if something's in A sub n plus 1 and it also improved and it's not a path anymore, so it must be negative infinity. So all of the A sub k's where k is at least n, right, contain vertices with negative infinite distance. Okay, that gets us closer. It doesn't quite resolve everything, right? So we know that everything that's in some A sub k that's at least n, has negative infinite distance. That doesn't tell us that everything with negative infinite distances in one of those sets, a slight gap. And not only that, but I don't really have time to compute a sub n squared or a sub 2 to the n or something, right? So, is there any way to get a more concise? So it is true that, yeah, so maybe some questions is is there some way to take that big set of a sub n plus 1, a sub n plus 2, all those vertices are improving at some point after the nth iteration, somehow get it something more compact so I can actually compute the thing. And at some level, how am I going to connect that back to the vertices with distance negative infinity? Okay, so there's still some gaps, is what I'm saying, but this definition is a help. Okay, so let's see. All right, so here's maybe a nice simple claim. So if I'm looking at the vertices that improved after 11 edges, or on the 11th edge, and I compare it to the vertices that improved on the 10th edge, okay, I know that every vertex that improved on the 11th edge, that 11th edge must be coming from someone improved on the previous round, right? Because if it was from 9 or something, that improvement would have come from in the previous iteration when I'm computing k equals 10. So if I'm improving on k equals 11, that better walk, that last edge is coming from a vertex that improved in k equals 10. Okay? So if I'm looking at like a sub n, and I look at all the neighbors of a sub n, where I start in a sub n, I take an edge outwards, and that's an out neighbor. I know that a sub n plus 1 is a subset of these out neighbors. Okay, so capital N to the plus is a standard notation for the out neighborhood of a set of vertices. Okay, so n plus a sub k means all of the vertices that I can start in a sub k and take one edge to get there. Okay, so it looks like this kind of picture. Okay, so I kind of can't really get to a sub n plus 1 except through a sub n, so to speak. Okay. All right, so with that established, then I know that, I meant to do that one at a time, but I know that, for example, so I know that a sub n, right, everything has distance negative infinity. And I know that a sub n plus 1 is a subset of everything that's one hop away from a sub n. And I know that a sub n plus 2 is a subset of everything that's 2 hops away from a sub n. I know that a sub n plus 3 is the subset of everything within 3 hops of a sub n, and so forth. Okay? So I know that all those sets are reachable from a sub n, right? So if you're in a sub n plus 1,000,000, I know that there's some way to get there from a sub n. That I know. Okay, so let me write that down. Okay, so that's right. So all those things in those bad sets, right now I know it's at least reachable from a sub n. Okay. Now let's look at the other direction. Suppose I have a vertex, V, that's reachable from a sub n. So S can get to a sub n somehow, and somehow you can get from a sub n, or some vertex in a sub n, to T. Okay. What do I know about the distance from S to T? What do I know about the distance from S to any vertex in a sub n? It's going to be negative infinity, right? Because it's more than n minus 1. Okay. So I can go from here to here with arbitrarily small distance, right? That's I know. So now, again, if I can go from S to T via some vertex in a sub n, then what do I know about the distance from S to T? It will be some kind of sum, and that sum is? Yeah, arbitrarily small plus some finite number. I get something arbitrarily small. Yeah, I mean, I can make this more negative before appending this, right? So Conversely, if t is reachable from a sub n, then dst is equal to negative infinity. Okay. All right, so now what's the punchline for our algorithm? Right. Punchline, that distance is infinity if and only if it's reachable from a sub n. All right, so if I know this, now let's go back to our original question. I have that dynamic program, I can choose k, but the graph may have negative cycles, it may have some negative infinities. How do I put this all together? What do I set k to, and what are the other steps involved? So some level, I just need to figure out a sub n, right? A sub n is going to tell me like everything I need. How do I compute a sub n? Yeah, for what value of k? I mean, how long do I have to run it? Yeah, sorry. K equals n, right? We run that dynamic programming algorithm up to k equals n, so I get all the walks of length up to n. I'll compare my answers from n minus 1 to n. Everyone that went down, they go into a sub n, right? From there, now that I have a sub n, how do I figure out everyone with negative infinite distance? From a sub n. So I can just do depth first search. You know, if I want, I can do, I'm sure you guys know this trick, but I can make my own starting vertex. Like I can add a vertex to the graph that is connected to every vertex in a sub n and call depth first search from this imaginary extra vertex I've added. So S star can reach all of a sub n, so anyone S star can reach is someone that a sub n can reach. Right? This way I only have to do one depth first search call as opposed to from every vertex in depth in a sub n. Okay. So basically the punchline is that before, if there's no negative cycles, I only have to run up to k equals n minus 1. If there's negative cycles, you just have to go up to k equals n. Then do some depth first search to figure out who's negative infinite, and whoever's not negative infinity, you've already computed the value. Okay, so k equals n suffices, so that gives you an m times n time algorithm. All right, any questions? Okay, great. All right, I think we have plenty of time for this last part. Okay, so let's move on now to the other part, all pairs shortest paths. This is actually less subtle. I think the negative cycles are hard to deal with. And I'm going to assume for simplicity that there are no negative cycles in the graph. Assume that's promised. You can detect negative cycles using the algorithm we just developed. And it's true that one or two of the upcoming algorithms will work for negative cycles, but not all of them. And we don't have too much time to separate the two. Maybe that'll be a good conceptual question. All right. Maybe a good exam question. Anyway, all right. So the challenge is to compute the distance from S to T for all pairs S and T in the presence of negative edges, but promise that there's no negative cycles. Okay. The simplest thing, of course, is we can just run our algorithm from before for all pairs of vertices, and that will give you m times n squared. If m is very big, like say m is n squared, that's n to the fourth. And in that particular extreme case, that's where we're going to try to get some improvement, particularly when m is larger than n. All right, so a natural idea was already suggested earlier in an earlier discussion. Why don't we just add s as a parameter as well, right? So we could just do that. Okay. Now that I'm interested in all pairs s and t, and not just like a fixed s and t, maybe there's some value to just doing all the s's and all the t's. Okay. And we can implement it basically exactly like we did last time, right? If I is equal to 0, then if s is equal to t, the answer is 0. I don't use any edges. If I is equal to 0, so I don't have any edges, and s is not equal to t, it should be positive infinity. And otherwise, I can try to figure out how to add one more edge, right? That was the strategy from last time. One more edge, one more edge. So, sorry. Okay, so this is sort of the same code as before, only inserting s, but it shouldn't be too surprising. It's really the same idea. Okay, what would be the running time of this algorithm? If I saved my answers, I applied dynamic programming. Well, there's two ways to do it. One's not as efficient as the other. One is, okay, we just need to go from 1 to n because we know that paths are enough, so I equals n is suffices. So n choices for s, n choices for t, n choices for I. And then each subproblem loops over a bunch of edges. There could be n edges, that gives you like n to the fourth, right? But we did something more clever last time. So one is, oh, that's fine, okay. Another is n choices for s, n choices for I, and in summing over all the choices for t, I'm summing over the in degree of t, like we did last time. So it's going to be n times m. Okay, so then you can get that kind of running time. All right, mn squared. And the question is, can you do better? Even with the same recursive spec. All right, I'll give you guys a quick chance to try to guess. The solution is cute, but maybe hard to guess. Any ideas of how to implement this recursive spec more efficiently? All right, here's how I would suggest. Okay, we know how to do I equals 1. Probably know how to do I equals 2. That's no big deal. Okay, let's skip 3. Suppose I want to do I equals 4. I want to get from S to T using at most 4 edges. And suppose I never computed I equals 3. I'm claiming you can figure out how to do 4 using 2, so to speak. So if you computed all the values for I equals 1, you've computed all the values for I equals 2, we're skipping 3, trying to figure out I equals 4. I'm claiming it's possible. Sorry? Get the neighbors of S? Okay, so I'm trying to get from S to T with 4 steps, right? So, okay, I can enumerate the neighbors for S. Oh, and also the neighbors for T. Okay, and then in between I can try to guess 2. Okay, that's actually not a wrong solution, but you can do faster. Let me give another one then. Okay, let's say you figured out 4. Let's say this is okay for 4. And now we're going to skip 5, 6, and 7. We're going to go straight to 8. Okay. Okay, so what would that be for 8? Okay. S and T. I'm trying to get from S to T with at most 8 edges. There must be some vertex in the middle, where on this side there's at most 4 edges, and on that side there's at most 4 edges. Okay. Now you can see how to do 16, how to do 32. Okay, so you can actually skip quite a lot of numbers. All right, so that's the idea. This is sometimes called a doubling trick, okay, because the idea is we're just doubling in the interest of time. Okay, I'll just show the code. So, all right, so in other words, instead of doing values of I, I'm just going to do values of 2 to the I, for I is equal to 0, 1, 2, 3, right? That's going to get me 1, 2, 4, 8, so forth. All right, maybe the only thing, well, one thing to be a little bit careful about is the base case, because when I equals 0, there's actually one edge. You can use at most one edge, so the base cases change a little bit. If S is equal to T, then the distance is 0. You can just stay there. And if S is not equal to T, but there's an edge between S and T, you can use that edge. And then finally, if S is not equal to T, but there's no edge, then you get positive infinity. So the base cases are a little bit different, okay, but same idea. All right. And now if I want to calculate 16, I already have 8, 4, 2, and 1, right? What the code is, well, I can either do 8, right? So I can either keep the previous number of edges, just like before, or I can split it in half, in which case we're going to guess. This is taking a minimum over all guesses of U. So this is not just neighbors of S anymore, right? This is all neighbors of U, all possible vertices in the middle, and splitting it up. Okay, 8 and 8 on each side. Okay. All right. All right, hopefully the algorithm makes sense. What is the running time now of this algorithm? Sorry? Mn log n. Okay, so let me break that down slowly. Okay, so at some level, what's the largest value of I will need? Log n. So, okay, once I get to log n, then I know I've covered all the paths and there's no negative cycles, so I'm done, right? Okay, so so there's log n choices for I. Okay, and you said mn log n. So I guess you're saying that there's n choices for S or something, and I'm trying to sum over the degrees for T or something. Okay, that's what we did before. But look at this code. Let's say that for fixed T, right? How big is that loop? N. So we're no longer actually just looping over the edges that go into T, because we're guessing all the vertices that could be in the middle. So we can't do this trick where we're summing up the degrees. All right, so that leaves us with, we can't do the degree trick, then the running time becomes, I heard n squared log n. Is that correct? How many choices for S? How many choices for T? N choices for T, n choices for S. Log n choices for I. Now for a fixed problem, how long does it take? There's a loop in there. How big is that loop? N. All right, that's actually n cubed. Log n. Okay, but still better than what we had. I think we had mn squared before. So if m is much bigger than n, then we get some improvement at least. Okay, m could be like n squared. Okay, and then just a simple trick, right? In fact, we didn't even change our sentence. All right, we have one more trick for all pair shortest paths. So what have we done? We can run that mn algorithm from every vertex, that's mn squared. We can do this doubling trick and add s as a parameter. That gives us n cubed log n. Okay, I'm going to try to do a little bit better. And this one's going to be different. Okay, this one's kind of funky. These all have names, by the way. The first one was called Bellman-Ford. The second one, the one we just did, is called, I'm not sure, it has a name. It's in the notes. The third one is called Floyd-Warshall, and names don't matter too much. Okay, anyway, they're all just ideas. All right, anyway, so we're going to do something different for our last algorithm for all pairs shortest paths. Okay, and the setup is completely different. Initially, I'm going to number all the vertices 1 to n, any order you want. V1, V2, V3, V4. The order doesn't matter. Okay. All right, and so here's sort of a funky, different kind of recursive spec. Okay. I'm going to think about going from Vi to Vj, but instead of counting the number of edges I use along the way, I'm going to limit the vertices I'm allowed to use in between. Okay, so SWIJK will be the length of the shortest walk from Vi to Vj, only going through vertices V1 through Vk. Okay, so, there's some walk from Vi to Vj. Okay. And all the intermediate vertices must be coming from the set V1 through Vk. Okay, so we're doing a different kind of induction. It's an induction on which vertices I'm allowed to use in the middle. We're not counting edges anymore. Okay. All right. How do I define what?
How to define sequence of V1 to the end?
Oh, initially, at the beginning, you can choose any one you want. Yeah, any indexing will fine. Just fix it, and yeah, any choice of indexing is fine. Okay. All right, so we can implement this together quickly if we have. Otherwise, I'll just show it on the next slide. All right, but let's try to do it because it gives us some practice. All right, so we have the base case is when k is equal to 0. Right, so that means I don't have any intermediate vertices. All right, in that case, what do I have? What are some of the base cases within the case k equals 0? Sorry? Yeah, there's only one edge between them. Okay, yeah, okay, so you only have at most one edge. So that's good. Okay, so if I is equal to j, so it's the same vertex, that should be 0. If vi, vj is an edge, then I can take the length of that edge. And then otherwise, there's nothing I can do, so it's positive infinity. Okay. All right. All right, now let's look at the inductive steps. So k is at least 1. All right, let's say k equals 10. So you know how to get all the shortest walks using vertices 1 through 9. Now you're allowed to use vertex 10. What does the inductive step look like? Yeah, going from Vi to Vj. So we have two choices, right? We can either use Vk or not use Vk. How do I model not using Vk? Okay, good. That's one choice. How do I model k? Right, so what happens if I do want to try using Vk somewhere in the middle? All of these vertices are coming from the set v1 through vk minus 1. Same with the other side. Okay, so we can do SW I k k minus 1 plus SW k j k minus 1. So I'm trying to get the k using all the other intermediate vertices from previous rounds. Okay. All right, that's the code. Now we just have to figure out the running time. We're done. This is the last bit. Okay. All right, what's the running time of this algorithm? Sorry. N cubed y. How many subproblems are there? How many choices for I? How many choices for j? How many choices for k? N. V1 through Vn. Okay. All right, we have n cubed subproblems. That's a lot of subproblems. That's more than before. Okay. How long does each subproblem take? Oh, 1. There's actually no choices. I mean, there's only 2 choices now. So although we've increased the number of subproblems, actually the code for each subproblem is very short now. It's just the 2 cases. And as a result, we actually get an n cubed running time that's a little better than n cubed log n using the doubling trick previously. Okay, so that's the best we've got for all pairs shortest paths, unless you're doing some other weird stuff. Okay, anyway. All right, so that's n cubed for all pairs shortest paths. That's all I had for today. All right, we're done. Thank you.